essentially what we're going to review today is different ways in which we can express lines in 2D and also 3D. So they're just kind of like new types of ways that we can express lines, kind of building off some of our vector knowledge and also some of our previous knowledge from like expressing lines in grade 9. So a couple things that we'll be going over are how to express vector equations of lines, parametric and what we call symmetric equations, and I'll show you some graphing software as well that can be useful to you. Lauren, can you just grab that back door for us there? Okay, so let's just start. We're going to do a little review here. I want to express the equation of this line in y equals mx plus b form. We're going to start there. Yeah, throwback, exactly. So, any thoughts? Who remembers how to do this? Okay, our b value is 3 because the y-intercept is 3. Lovely. Okay. What else? What other information do we know? What is m?
The slope.
Okay, so we need rise over run, right? So if I choose like 2 points on here that I know for sure are on here, I would say my rise is -1 and my run is 2. So this is going to have a slope of -1 over 2. Agreed? Does that make sense? Okay, so we're just looking at the rise and the run between two known points on our line. Okay, so that's our y equals mx plus b format. If I wanted to express this in what we call standard form, essentially this means I want all things moved over to one side, and ideally what we like is to have, we kind of get rid of fractions in doing that as well. So that's my y equals mx plus b, but if I move forward from there, and I try to move everything over to one side, usually we will aim to have maybe like no fractions, so kind of get rid of that fraction. So I'm just going to come through here and I'm going to multiply each term by 2. And of course I can do this over on the 0 side as well, but that doesn't really make much of a difference. And then we'll see that the 2's actually cancel each other out here, so we're just left with x minus 6 equals 0. So, and then usually it would be like ax plus by plus the c value. So we usually express it in this format right here. So similar to how we have various equations for representing kind of like regular lines in 2D space, we're going to have methods of expressing lines in terms of vectors in both 2D and 3D space. So I might jump back to this slide. Maybe we'll just go on dual page here. Excuse me. Okay, so our task is to find the vector, parametric, and symmetric equations for our given line here. Our vector equation, oh, why am I cut off over here? It's weird. Is yours cut off on yours? It's not. Sorry, I just made it too wide now. I'm struggling. There we go. And it's still cut off. It's so weird. So weird. Okay, well, I'll just read it to you. Sorry, I'm like losing my voice here. So vector equation is going to be the equation that describes all vectors from the origin that end at a point on the line. So any possible vector that could start on the origin and end on any point on that line. And it also consists of a position vector, which is essentially what I'm saying, so the vector that goes out to one point on the line. And it's defined by a direction vector, which is essentially a vector that also starts at 0, 0, but has the same slope as our line has. Okay? So if I know a point on the line and I know the slope of that line, or I have a position vector, or not a position vector, but a direction vector that is parallel to that line, that specific thing is going to define my line. So essentially how we're going to express this for our vector equation in 2D is we're going to call it R, vector R. And this is going to be R naught, which is going to be our position vector. And this is essentially going to be the vector that goes from 0, 0 out to a point on the line. Oops. Okay, and then we have some parameter t, which essentially just means like it can be a scale multiple of this vector. And then we'll have our m vector, which we consider to kind of be, we call it m because it's kind of taken from slope, and that tells us our direction. So this will be our direction vector. Okay? The t essentially just means like it can be any scale factor of this direction vector. Okay, so for our position vector, let's just say probably one of the easiest things that we can do, even especially if we have like a y equals mx plus b equation already, is just use the y-intercept as our position vector. So I'm going to say our position vector will be the vector that goes from 0, 0 out to the point 0, 3 on the line. Okay, we'll call that R naught. But keep in mind, I could, like I'll show you another variation of this at the end. I could choose anything that goes from the origin out to a point on the line. As long as I know what that point is and I'm not having to estimate it, would be ideal. Okay, so this is the vector that we just drew. It's the vector that can be represented as the vector 0, 3. Okay, and this is the vector that, again, goes from 0, 0 out to the point 0, 3. That's what we're saying. Okay, t is going to be a parameter that remains, and it's essentially just saying it can be any scale multiple of that direction vector. And then I need a vector that starts at 0, 0 that is actually parallel to my line. So essentially, it kind of has to have the same slope as my line. So this vector right here that has the same slope as my line goes from here to here. You'll notice that it goes down 1 and over 2, just like the slope of our line does. So if I have a vector that goes out and is parallel, so you'll notice again, if I drew this vector up here, it would actually be kind of like a vector on my line. This is kind of like our direction vector here. How can I express that vector? 2, negative 1, yeah. Okay, so you'll see that that direction vector actually has my rise as my y value and my run as my x value, okay? So this is going to be like our rise and our run. Okay, so just so you guys know, this is one way that we could express this line, but we could also have other possible equations. So another possible equation, maybe we want to use the x-intercept as one of our points for our position vector. I could use the point, I don't know, what else is on here? 4, 1. I could definitely do that. So if I wanted to use maybe a position vector as this vector out to the point 6, 0, I could say R equals 6, 0, the vector 6, 0, and then the same direction vector, so 2, negative 1. Okay, so there could be multiple ways that we could express the equation of this line. Lewis? Sorry, say that again. 2, 2? No, because 2, 2 is not it has to be parallel to the line. So 2, 2 is not parallel to the line. Doesn't give me the direction of that line. Mark?
So R naught can be any point on the line, basically?
the position vector from 0, 0 out to any point on the line. That's right. Okay? All right. We're going to do parametric and symmetric on the next page. Okay. A set of parametric equations can be found by isolating each coordinate of the vector equation. So essentially, I express the x components and the y components in kind of like two separate equations. So I'm going to work off of my original one. I'm going to work off this guy. But again, be aware, like, if I have a different line that I created from that, like a different position vector, I can do the same thing. So the parametric equations are going to be x equals and y equals. And then essentially I'm going to say the x components, which would be 0 and 2t. And essentially we would have this. Okay? And of course I don't really need to put the 0 there, so I can just say x equals 2t. And then for the y one, I'll have the y components here with that parameter t as well. So it will be 3 minus 1t for y. Okay, so you'll see here that the components are kind of broken up in terms of x and y. These first guys right here will be our position vector points, x and y. And then you'll see these points over here, the 2 and the negative 1, being our, sorry, that's kind of hard to see. Maybe I'll just put the actual 1 there so that everyone can see it. The 2 and the negative 1 are taken from our m vector, or our direction vector. Okay, so just splitting them up into their x and y components is essentially what we're doing. Okay, so the final parametric equations would be x equals 2t and y equals 3 minus t. Okay, and then the last one, the symmetric equations, can actually be found from the parametric equations. So it's kind of like a substitution thing here. We know that the t parameter is actually the same in both cases because it's obviously coming from the same vector equation. So what we do is we take our parametric equations and we isolate for t, and we kind of set them equal to one another. Because if I know t in terms of x and t in terms of y, then I'll know that those two things are equal. So I work to take x equals 2t and to get t by itself. So I'll get t equals x over 2. And then I'll work to get t by itself in this equation over here, which means I'm just swapping the t and the y. And because I have t equals x over 2 and t equals 3 minus y, I can actually set these guys equal to one another because they're both equal to t. So these are called the symmetric equations. Okay, so I think it's easiest, and when I say parameter here, by the way, I mean the t value. So I think it's easiest if you're going to get symmetric equations to just get them from the parametric equations rather than trying to like figure out how all of that is connected. So get your parametric first, and then you can get your symmetric from there.
Would it still be like parametric if, say, you use the symmetric?
I mean, we technically could, but we don't usually do that unless we're like using it to solve for something in particular. But yeah, we'll usually keep it separate on each side.
So that's like the y equals mx plus b formula.
Yeah. Yeah, so that's actually a good point. This is, Mark just made the observation that this is actually kind of like our y equals mx plus b formula rearranged. So we can see that the components that we have that deal with y's are actually over here, like the negative part and the 3. And then we can see the components dealing with the x are actually over on the other side here. It's a good observation. Questions so far? Okay, we'll do some practice with setting that types of stuff up. Okay. All right. Scalar equation, or Cartesian, sometimes called Cartesian equation for the line shown on the previous page. So this is for 2 space, and it's in the form where the vector that is a normal, or it's essentially perpendicular to the line, is actually used. It's kind of a similar setup to our scalar or standard form equation for our regular line. Devin?
Can you just explain, oh, just kidding. Wait, why is this like x and y? Wait,
So we're essentially just taking our vector equation that we have here,
yeah.
and we're splitting it up into the x components, and then we split it up into the y
And then
components.
here you just made it x equals, because it's 0, so it's just 2.
Yes, yeah, exactly.
And
Okay.
where'd the t equals x over 2?
So for the symmetric equations, what the deal is that for parametric, we actually isolate for the parameter, which is t. And then if I have t equals x over 2 and t equals 3 minus y, I set them equal to one another. So here in these 2 equations, I'm taking them from above, my symmetric equations, and I'm isolating for t and setting them both equal to one another.
Okay.
Okay? Okay, so here's what we should expect. When we're doing scalar equation in 2D, I should actually expect to get this standard form equation. And you might be asking me like, okay, well, why don't we just find the standard equation? Sometimes we don't have that actual line on our page ready for us to find the standard form equation of the line. So sometimes we have information about the direction vector, the position vector, and stuff like that. So I'm going to show you how we're going to end up at this scalar equation, what we call scalar equation, when we're working with Cartesian vectors. Okay, so we actually want, so just to remind you, we call this R, but you'll also see it with the notation like xy, where you have that position vector from before, plus your direction vector from before, with your parameter. So when we express the scalar equation or Cartesian equation of the line, what our goal is to actually find a normal equation for our direction vector, or find a normal vector for our new equation to the previous direction vector. So we're going to find a normal vector. And essentially that just means it's perpendicular to our direction vector. So there's 2 ways that we can express the direction of our vector, right? I can do a parallel line, or if I express it as a perpendicular line, that's also a way that we can express a line. It still will define our line if we know either it's parallel vector or it's perpendicular vector. 2 different ways. So here's a little trick that you can do. I'm just going to do it over on this side over here. You can actually take your direction vector, okay? And the quickest way that you can find a normal, I mean, you can choose things where you set the dot product and set it equal to 0 and then solve. But the quickest way is to actually swap and change just one of the signs. So you're going to swap the x and y coordinates. So essentially, if I swap, I get -1, 2. So one option could be if I switch the -1 to +1. So 1, 2 could be a normal vector. Or if I swap the coordinates and I make the +2 negative, I could also have -1, -2. Okay? You can always check your work by dotting it and just ensuring that you get 0. So we can actually probably see here, if I do 2 times 1 plus 2 times -1, that gives me 0. And then if I do 1, -1 times 2, plus -1 times -2, that also gives me 0. So the dot products of those two things are 0, telling me that these are, in fact, perpendicular vectors. Okay? So that's a really quick way that you can find a normal vector. So I'm just going to use the simpler one here. I'll just use the positive version, 1, 2, as my normal vector. And then this is kind of like our scalar equation. So essentially, like our standard form equation of a line. This is for 2 space. So it'll be, I don't have a z component to this. It's just going to be ax plus by plus c. And our normal components actually go into these 2 spaces right here. So it will be 1x plus 2. Or again, if you're using this vector, you can do that as well. It can be -1x minus 2. And then our job is actually to solve for the c with a point on the line. Okay? So that's where we define that particular line. Because if I have a normal vector, okay, this is in 2 space. If I know a normal vector, my line can be anywhere except for as soon as I define it with a point, my line is stuck, right? So as soon as I know, oh, the point has to be here, then my line can no longer slide anymore, right? It has a specific point where it's like, okay, this is where the line is. So if I have the normal vector and a point on the line, that defines the line. I can also have a parallel vector, a direction vector, and again, a point on the line. So again, these can be parallel anywhere, but as soon as I have a point on the line, this stops, right? And I know exactly where that specific line is. So we need a point and a direction vector, or a point and a normal vector, okay? Either of those combinations work. So we know our point on the line based on our vector equation here, or again, if it tells you such and such thing is a point on the line, then we know that as well. So we'll sub in a point. Okay, we're going to use 0, 3 in for x and y. And this is just so that we can find that c value.
Why 0, 3? Is that 'cause we, oh, that's the, okay.
Yeah, but it could be, again, we could use 6, 0 if we wanted to. Any point on the line is fine. So we'll get c equals -6. And then our final equation is x plus 2y minus 6 equals 0. And that is considered the scalar equation of our line. So it contains a normal vector, and it contains a point in there to solve for c. Okay, and you should notice that this is actually the same as our previous standard form equation. Again, this is just given some vector information, how we can express the equation of a line in vector format.
Even though like it's in vector format, like it still looks like
Yeah.
a normal.
Yeah, so this would just be like, we would use this essentially if it asks for, so scalar equation. And then you might be given some information such as it gives you a position vector, and then it says, it gives you a point on the line, and then it says find the scalar equation, right? So in this case, yeah, we could have found it. We had the picture of the line, so we could have found it a variety of different ways. But sometimes maybe you'll just be given some different types of information, and then you need to know how to get there from, or maybe you're even just given the normal vector and a point on the line. That's going to be harder to find, like try and like graph the line and all that kind of stuff, right? This is kind of the route that we would take in that case.
And like T stands for like parametric.
So T is what we call a parameter, and it essentially just means, like if I slide back to our very first thing here, it essentially just means like any scalar multiple of this direction vector. So it's just saying like it can be any size, really.
And like our M vector, does that like stand for like what does the M vector stand for?
So the M vector is the direction vector, so it has to be parallel to our line. It's a vector that's parallel to our line. And we have the T because it can be, again, any scalar multiple of that parallel line. Okay? Okay. Going into 3D. For 3D, we have our vector equations, we have parametric, and we have symmetric. And it's going to pass through the points. I don't know if I have it underneath here. Probably not. It's going to pass through these points right here. Let's say we have point A, and it's going to be 2, -1, 3, and point B, 5, 1, 1. Okay, so before we find this, I actually want to show you guys, I was playing around with, it's called GeoGebra. It's a 3D graphing software. So I'm just going to delete a couple things out here. Actually, I'll just delete it all out so I can show you guys. So if you just Google GeoGebra 3D graphing software, you'll kind of see here that you can actually move this around. So the red is my x-axis, the green is my y-axis, and the blue is my z-axis here. So I can actually graph these 2 points that I just showed you guys on our lesson. Okay, so there's my point A. It's in 3 space, right? So it's kind of like out. We'll graph our point B as well. So capital letters, if you're using this software, capital letters are points. Lowercase letters are going to give you a vector out to that point. So I'm doing capital letters for our points here. So 5, 1, 1. Okay, so there's our 2 points. Our point A, maybe I'll just change the color of this so we can see. Okay. So there's our 2 points. I want the line in 3D space that connects these 2 points, okay? So I can actually go over here and I can choose line, and I can actually select the 2 points that I want the line to extend to. And there's my line right now, right there. I just created it. And it actually creates the equation of the line for me. So you guys can kind of see here that we have 2, 1, 3, which is a point out to the line, a 3D point on that line. Okay, you can kind of see it in 3 space here if you want to check it out. So I've got a point. And then I have this direction vector. Now, I want you guys to see if you can kind of figure out, can everyone see this okay? It's the direction vector 3, 2, -2. Where does that come from with my points A and B? How would I get 3, 2, -2 from our 2 points that we just started with? Yeah, so it's B minus A. So if I'm doing the line from A to B, I'm going to do B minus A. I could also technically express this as the reverse vector, like I can say -3, -2, and +2, and the line should remain unchanged. Yeah.
Why is it pi?
That is lambda, and essentially lambda is like our t. It's our parameter t. So this graphing software just essentially uses that as the parameter for the direction vector. Okay, so going back to our points here, I want a point, so I want a position vector. My position vector can be one of 2 things. It can be OA or it can be OB. And the other thing that I should mention on here is that you might notice in some notes that you stumble upon if you're like studying online that people actually don't use square brackets for vectors. So these 2 things are actually both vectors. So just be mindful that sometimes vectors are expressed with round brackets. So we try to make the distinction by using those square brackets, but yeah, this software in particular uses round brackets for everything. So. Okay, so let's just say we use OA as our position vector. It's from the point 0, 0, 0 out to a point on the line. We know 2 points on the line. We can do OA or OB. And we know OA is essentially just like the vector made from point A. That's going to be our position vector. So we usually call that like R initial or R naught. Okay, and then I need a direction vector, which is going to be made from, if I have points on the line, it's going to be made from 2 points on the line, unless it's given to me. So I just need my direction vector. Let's say we found in our graph above that we found the vector AB. And that's essentially just going to give me the vector that's parallel to our line so that we know that position and then also the location and slope of that line. So we said we can find this by doing 5 minus 2. Okay, tip components minus tail components is what I'm doing. 1 minus -1 and 1 minus 3. So we get the direction vector 3, 2, -2, which is what you guys saw on the software previously. Okay, so our final vector equation of this line in 3 space is going to be expressed very similar to how we express in 2 space. It's going to be r, and again, sometimes you'll see this notation where it says like x, y, z, and then I'll have our position vector, or r naught, plus our parameter t, and the direction vector. Okay, so this AB, this is going to be our m vector. Okay, so same equation as before. Again, this is our r naught vector, and this is our direction vector. Okay, from there we should also be able to develop our parametric equations and our symmetric equations. So we're just going to practice that same deal as what we do in 2D, except when I have parametric in 3D, I'm going to have not only x and y, but also a z1. So I'm going to take the x components here with the parameter t, and our first one will be 2 plus 3t. Our second one, I'll take the y components with that parameter t still. So it'll be -1 plus 2t. And then I'll take the z components. So I'll have z equals 3 minus 2t. Okay, and then for symmetric, I want to take each of these and isolate for t. So I'm actually going to have 3 equations that are set equal to one another. So I'll have the one where I isolate in the x equal to the one where I isolate for t in the y equal to the one with z. Do I need to show the isolating of this? Okay, so I'm just moving these things over. So this is, the first one will be x minus 2 divided by 3. The second one will be y plus 1 over 2. Okay, I'm just imagining that I'm isolating for t in each of these. And z minus 3 over -2.
And they all equal each other because they all equal 2.
Yeah. Okay, so those are 3 different ways that I can express my vector equation of a line in 3 space. Just as a little note, there's no scalar equation in 3 space. Scalar equation is only for lines in 2 space. As soon as I have like a scalar equation in 3 space, I'm actually representing the equation of a plane. So no scalar equation for 3D vectors. Okay. Y equals mx plus b and ax plus by plus c equals 0 are representations for lines in 2 space only. Sorry. Okay. All right, so that's pretty much it for today. There's lots of things that I'm going to kind of show you on this software. If you want to use this to kind of check your work as you're working, I did download an app, but I didn't have a chance to see if it works well. I downloaded it on my iPad, but you can just, again, Google GeoGebra and kind of play around with it. Some of the stuff is a little bit hard to enter, so you might have to watch some videos to see.